A big part of linear algebra is understanding the structure of collections of solutions to systems of linear equations. So I wanted to start out just by looking at what can happen when we have several linear equations and we put them together to get a collection of solutions, just to see geometrically what can solution sets actually look like. And there are only a few situations where we can actually draw pictures to understand the geometry of how these solution sets are put together. And we're going to start out with probably the sort of linear system that you've seen before. This is a linear system that has two variables, and we'll start out with a two-equation system like this. So this is the sort of thing that you would have solved in any number of previous math classes. And one key thing about a system of equations is that each equation in the system sort of somehow slices through the possible collection of solutions and gives you a slice. And a solution is where all those slices intersect. So for this particular system, since we have two variables, we need an axis for each variable. So there's an x-axis and a y-axis. And so the resulting geometric space, which in this case is the xy coordinate plane, the resulting geometric space is all of the possible solutions to this system of equations. Of course, not all of these possible solutions are actually solutions, and locating and characterizing the actual solutions is really a large part of what linear algebra is all about. For this sort of two-variable situation, we have good tools already for solving this kind of system. So we could start out just by graphing each equation. So each equation, if we draw these solutions for each equation individually, we're going to get lines. So we could put this into slope-intercept form to graph this. So say move the x over, then divide by -2. We're going to get, I guess, y equals 1/2 x plus 2. And so that's going to start at 2 and go over 2 up 1, over 2 up 1. So something like this. About like that, almost. So that's the first line. And then for the second line, we can do the same thing. Put this into slope-intercept form. So this is going to give us y equals, I guess, -3/2 x plus 6. And this one I'll do in red, so the y-intercept is at 6, and so we need to go over 2 and down 3, over 2, down 3, and this gives us our second line. So each equation has its own collection of solutions, and then the two equations together have a solution that satisfies both equations at the same time, and geometrically that's where the lines intersect. Right, so this particular system of equations has one single solution, which is just this point. It looks like it's 2, 3. And we can check that this really is a solution by putting it into the original system just to check that it actually works. Right, this is what a solution really is. A solution to a system of equations is a value for each variable that makes each equation true. And we can check that this really is the case. So in the first equation, replace x with 2, -2 times, and y is 3. And then we check, is that equal to -4? And yes, this is 2 minus 6, and that is equal to -4. And then we can check the other equation, 3 times x, and x is 2, plus 2 times y, and y is 3. Is that equal to 12? Yeah, this is 6 plus 6. That's equal to 12. Yes. Okay, so this really is a solution. So this is one possible form that a collection of solutions to a system can take. We could have just a single solution like this. To get a handle on the other kinds of situations that can pop up, let's just think for other two-variable systems, what could happen? Well, there are a few situations. I mean, we could have one equation. This is my abbreviation for equation. If we have one equation, that looks like just a single line, right? Remember, every equation sort of slices the possible solution space And so if we slice the plane once, we get a line like this. So in this case, we get infinitely many solutions. Every point on this line is a solution to the one equation that we have. So we get infinitely many solutions. This is my equation for, or my abbreviation for solutions. So that's if we only have one equation. That's not especially interesting. Let's see what happens if we have two equations. If we have two equations, the most typical situation, remember each equation is a line, and the most common situation is your two lines intersect. Right? Any two lines that aren't parallel intersect. So in this case, we have exactly one solution. Okay. What are other geometric configurations of two lines? Well, it's possible that the two lines are parallel, and in this case, there are no points that are on both lines. That means there's no solution to the system of equations. So in this case, we have no solutions. The other possible configuration of two lines is that you have one line, and then the second line is actually the same line like that, in which case every point along this line is a solution because every point along this line is on both lines, since it's really only one line. So in this case, we have infinitely many solutions again. All right, so that's if we have two equations. We can only have one solution, no solutions, or infinitely many solutions. Take a second to imagine moving these two lines around in the plane and trying to produce any other collection of solutions besides one solution, no solutions, or a whole line's worth of solutions. If you try, you'll see that it's not actually possible. There's no way we can have two lines that intersect in, say, 2 points. So these are really the only possibilities for two equations. Let's look at three equations. So three equations in two variables. That means we're going to have three lines in the xy plane. That would look, let's see, in general you'd have something like this. And although these lines, they do all intersect each other in pairs, there's no single point where all three lines intersect. And so a system of three equations like this would have no solutions. It is possible to get just one solution if you have all three lines that sort of by coincidence almost, just happen to all go through a single point. So in this case, there's exactly one solution. Of course, if you have all three lines piling on top of each other like this, so the same line three times, then you have infinitely many solutions again. Okay, now the important thing to notice about this three equation situation is that the typical configuration of lines, the typical situation, is actually the situation where there are no solutions. If you just pick three random lines, they probably won't all intersect in a single point. And this is in stark contrast to the situation with two equations. If you only have two equations, then the typical situation is that you have exactly one solution. So the important thing here is just by changing the number of equations, the typical collection of solutions can change. In fact, even with only one equation, the typical collection of solutions is infinitely many solutions. So it's not just the number of variables that can influence what the collection of solutions looks like. It's also how many equations you have. All right, so this was all with two variables. Let's see what possible collections of solutions we can get if we have three variables instead of two. So if you have three variables, remember you're going to need we could call them x, y, and z. You're going to need a coordinate axis for each of the three variables. So you need an x-axis, and a y-axis, and a z-axis. And this is sort of my attempt to make this look 3D. You should imagine that the x-axis is coming out of the screen towards you. And in this situation, you can see the collection of possible solutions aren't all the points in a plane, it's actually all the points in a three-dimensional space. One equation is going to slice this three-dimensional, one equation is going to take a flat slice of this three-dimensional space, and a flat slice isn't a line anymore, now it's a whole plane. So if we have only one equation in three variables, then we get a whole plane's worth of solutions. So this is infinitely many solutions. But when we say infinitely many, it's not just that there are infinitely many solutions, because it's actually a whole plane's worth of solutions. This is very different than the two-variable case, where we often had infinitely many solutions, but it was also always just a line full of solutions. It was never a whole plane worth of solutions. So in the three-variable case, it's possible to get a whole plane's worth of solutions. All right, now let's see what can happen if we have two planes, or two equations, which will correspond to two planes, of course. So two equations. So this is going to correspond to two planes, and that's going to look something like this. This is a little tricky to draw, but I'll see if I can do it. So like this. There we go. So this is a pretty typical configuration of two planes, and you can see that these two planes are going to intersect along this red line here. Of course, I've just drawn a portion of these planes. Really, they extend infinitely far, and so the line along which they intersect also extends infinitely far up and down. It doesn't actually end. So in this situation, we have infinitely many solutions again. Infinitely many solutions, right? But this time, this infinitely many isn't a plane, it's actually a whole line of solutions instead of a plane of solutions. So even though there are infinitely many solutions, there's some sense in which there are more solutions in the case of the plane full of solutions than there are in the case with a line full of solutions. So one of the things that we're going to have to wrestle with is how is it, or what is the right way to describe this difference in the size of the collection of solutions? Right, the plane versus a line. Because they're both infinite, but there's some sense in which the plane is bigger. So this is one possible configuration when you have two planes. Another possible configuration when you have two planes is that the two planes are parallel, like this. In this case, there are no solutions. All right, but is it possible to get just one solution? Well, imagine taking this diagram with two planes and just moving the planes around and try to picture how they intersect. Do they ever intersect in exactly one point? If they intersect, do they always intersect along a line? Well, you'll find that actually they always intersect along a line, if they intersect at all. So that means with just two equations, there's no way to get exactly one solution. So this is very different than in the two-variable case. And that's something we'll have to think about later in the class as well. Okay, so if that's with two equations, what if we have three equations? So this would be having three planes slicing through space. So that might look like this. So here's one plane, and here's another plane standing up vertically, and here's a third plane also standing up vertically. So each of these pairs of planes, so if we look at the two planes on the left, they intersect along this red line. And if we look at the two planes on the right, they intersect along this green line. And if we look at the two planes that are standing up vertically here, they intersect along this blue line. But all three of these lines actually intersect at this point, sort of back in the corner. So in this situation, these three planes actually intersect at this single point. So in this case, there's exactly one solution to a system of equations in 3 variables and 3 equations. All right, what are other possibilities? Well, if we have 3 planes like this, but 2 of the planes, or maybe we have 3 planes like this. So there's 2 of them like that, and then maybe there's one that goes across the back like this. These planes all happen to intersect at this line back here. This is as if there's a book that we've opened up, and the back plane is the cover of the book that's horizontal, and then these front planes are pages of the book sitting out. The back of the book and the pages of the book all intersect along the spine of the book. So in this case, we have infinitely many solutions. In this case, when we say infinitely many solutions, here it's not a plane worth of solutions, it's actually a line worth of solutions. So again, it's possible to have infinitely many solutions, but in different shapes. There are other configurations of 3 planes that we should think about. So for example, we could have a plane like this, and then a plane like this. So these first 2 planes intersect through here along this red line. And then we could have another plane that sort of slices across the bottom like this. And this would intersect the first plane, I guess, here. And the second plane, it would intersect there. Well, you can see that as long as these 3 planes aren't all sort of narrowing in towards each other, they aren't going to intersect in any single point. So this is another situation where there's no solutions. Of course, we could get no solutions by having some parallel planes. If 2 of our 3 planes are parallel, even if the third plane isn't parallel, like this, but if 2 of the planes are parallel, then there's going to be no single point where all 3 planes intersect. So here there are no solutions. And then maybe the final configuration is if we have a plane, and then our second plane is the same as our first plane, and then our third plane is the same as our first plane as well. In this case, we're going to get infinitely many solutions. But in this case, infinitely many means a whole plane worth of solutions again. So even if you have 3 equations, it is possible to have different sizes of infinitely many solutions. So figuring out sort of how all the geometry of this works is going to be one of our big jobs for linear algebra. It's not the only topic that we'll tackle, but it's definitely something worth investigating. As we solve systems of equations, keep in mind that this is really the general situation. You can have infinitely many solutions, but your infinitely many solutions might come in different sizes. You might have one solution, or you might have no solutions at all. Those are really the only possibilities. In 3 variables, we've sort of drawn every picture that it is possible to draw, but linear algebra gets really important when there are more and more variables, but we can really only draw pictures when there are 2 variables or 3 variables. But we'll do lots of examples where there are more variables than that. It's not uncommon in applications to have actually thousands of variables. Of course, in those cases, you ask a computer to do the heavy lifting on crunching all of the numbers. But the geometry of the situation is, even in those high-dimensional cases, the geometry of the situation is still the same. Each equation in your system slices through your space of potential solutions to give you some sort of plane or hyperplane in higher dimensions. And a solution is where all of those hyperplanes intersect. And the possible number of solutions is 0 solutions, 1 solution, or infinitely many solutions. And your infinitely many solutions might have various sizes depending on how exactly everything intersects.